Right. So today, so we want to finish our OS topic. Remember, we have a small part in the logic also, but first we'll finish the OS part. So then others, because OS is a small topic, then another topic is also over. Then we will finish the logic and we'll do some past paper questions on both. Okay. Maybe next time we can do past paper because today also we have a big topic. Subtopic. Okay, so last time we discussed about the process management. We didn't finish it, but we did good part of it. Okay, so and also we did discuss the file management as well. So when it comes to process management, we discussed that process is a running program, right? Running program is called a process. The computers are now, modern computers are multitasking. So multitasking means at a time we feel like multiple things are happening. So it is done by two things. That is, modern computers have either multiprocessors or multi-cores or even multiple logical processors. Right? So that means physically or logically there are multiple processors. So therefore different processors can be executed by different processors. The second mechanism is your operating system. This is hardware level. Your operating system do something called scheduling, where it gives time slots to different processors. So therefore, say process 1 is given a time slot, then B, C, again A. So therefore, we feel like all ABC is running, but actually at a time only one is running by one processor. So we were discussing about this because this is pretty much something under the operating system's control, and we discussed what are the different processor states and under which conditions or under which circumstances they move from one state to the other state. Right. So this diagram we discuss when a program or when a process is started. I told you that there are three ways a process can be started. The user start a program by running it, double click or whatever. That is one. Or another program may run a process. Maybe one program start another program, like at least sub program. The third one is scheduler. Operating system has a scheduler. So if you have scheduled any task, when the time comes, the operating system will do it. So that is also another new process is started. So when a process is started, it goes to the new state. So that means still it has not run, but it has signaled that I need to be run, okay, to the OS. So then once it is admitted to the queue, we call it is in the ready state. It is in the ready state. It can't straight away go into running. So why, just like other processors, now your process is also in the ready state. So then the operating system may pick processors to running by giving time slots. So when a particular process got the time slot, it is in the running state. Once the time slot is over, it has to go back to the ready state because a different process will be now in the running state for a one processor. Okay. So it will happen over and over, right? Until your program is or your process is released to the exit state. So I told you there are a few ways it can goes to this state also. Naturally, it is terminated, finish, done, or user has terminated it, or it has encountered an error, which therefore it can't proceed. So those are the three main ways the program can go into the exit state, right? So that is this part. So then we discussed that if the program comes to a situation where the user has to give attention or any other device, we call them input-output operation. So then until that attention is given to that process, it can't do any more processing or running. So therefore, once it reach to an input-output operation, your operating system will put it from ready to block state. Right, ready to block state. Actually, it will be taken from not ready to block state, running to block state. Okay, running to block state. And once the user attention is done, it goes from block to the ready state. It can never go from block to the running state. It comes from running to block, but it goes from block to ready. Okay, so then this part is over. So likewise, you must have a 100% clear idea, and if you have any doubts, you have to ask and clarify. So then we discussed that there's another possibility. If the computer is running low memory, there's something called virtual memory. Part of the disk is considered as sort of a virtually the memory. But this, because it is virtual memory, if it is in the virtual memory, it can't be accessed unless you again take it to the real memory. So therefore, if time to time, your computer might, or your operating system might decide to take a memory segment or memory part related to a particular process into the virtual memory. If it is taken to the virtual memory, now it can't be taken to the running state because the memory is, you can't, when it is running, it may try to access the memory, but that memory part is now in the virtual memory. So therefore, if it is taken to the virtual memory, any of the page, your operating system take that process from ready to ready suspend. If it was done, or if it is done while it was in the ready state, while it is in the ready state. So we say it is suspended because it is now in the virtual memory. But again, when the operating system feel like, okay, now I can give this process attention, so it will take it back to the ready state. It can never go back to the directly to the running. It has to come to always, if you go to another state, you have to come back to the ready state. So a process can go to the suspend and come back to ready, maybe different, maybe several times as well. And the same thing can happen while your process was in the block state as well. It is in waiting for a input output operation, and now operating system has decided to put it into the virtual memory. So then it can go from block state to the suspend. So therefore we just call this ready suspend and this one block suspend. And again, if the memory issue is resolved, it can come back to the block state. But while it is in the block state, suspend state, if the use attention or the input output operation is over, it will go to the ready suspend state. And again, when the memory issue is over, it can come back to the ready state. Right? You can see it can, sometimes it can go like this and come back here. Sometimes it can go like this, go like this, go like this, and come back like this. Right. So that is where we stopped. So that is where we stopped. I just repeated it because this is super critical. This is extremely critical that you know A to Z about this. No doubt about it. Okay. So you must be able to justify each and every transition. Okay. Right. So now we are going to discuss a little bit of extra additional things. This is not directly mentioned in your A-level ICT syllabus, but I always do a little bit of additional things because then your confidence is over, confidence is higher, right? So we can classify processors in different ways. This is one classification, this is another classification. One classification is CPU bound processors versus IO bound processors. So CPU bound processors means processors or programs which need a lot of processor attention. So that means it needs a lot of calculations, processing. So those kind of processors are called CPU bound processors. Right? For example, it can be a complicated calculation, right? Something like that. And also there's another notorious CPU bound type of process, that is graphic processing. So in order to do graphic processing, you need a lot of processing power. So that is why most of the time now modern computers have two processors, the general processor and GPU, CPU and GPU, like graphic processing unit. Why? Graphic processing needs heavy processing power. Right. So if whether it's graphic or whatever, if it needs a lot of processing power, we call them CPU bound process. But sometimes there are some processors which are mostly idle, right? But then and there you need to do processing, especially those applications where you need a lot of input and output, especially the interaction with the user. So there will be a screen, and until the user enter the data, it is waiting. Nothing to process actually. Very little to process. So those are called IO bound processors, right? IO bound processors. Okay. So CPU bound, IO bound. For example, I will go to my task manager. Right. So you can see here, my processor is 23% is average, on average, 23%, about 20 to 30% is utilized now, right? You can look at it from here also. You can see on average about 20-30% is used. It's not going to 100%, and it is not very low also. So that means my processor is utilized by different programs right now. Okay, but if I go to the processors tab, and you can even order by CPU, okay, you can see that right now Zoom meeting is taking the most of the processor attention, because now we are having a Zoom meeting session, right? So my side is the one that is recording and sending to you. I told you that Zoom meeting is a graphic because it's mostly my screen and bit of my audio. So you can see it is taking a lot of my CPU's attention, right? The biggest share is taken by that. So therefore, definitely my Zoom application, if it is running, it's a CPU bound process, right? CPU bound process. Okay. But if you go down, no, if you just take it the other side, right? So there are most of the processors, they are taking 0%. They are 100% idle. Right? Some background processors, etc. So those are pretty much IO bound processors. Okay, IO bound processors, and you can see the GPU separately also, and obviously Zoom is taking the good part of GPU and also my Windows manager, because it is rendered in the file explorer and other things. Okay, and not only that, you can even check the memory, which process is taking the largest amount of memory. For example, right now Edge is taking the largest share of the memory, then Firefox, then Zoom meeting, then I have the Eclipse running, so that is an IDE and those things. Okay, so but there are some other processors, they are hardly taking any memory at all. Okay, so then the disk access, how frequently it access the disk, right? So that you can see most of the processors 0, but there are some processors which access the disk, and also you can see Zoom is accessing disk because mainly it is saving recording the meeting. So of course, when it is recording, it has to keep writing it in the file. Okay, and some other system process, and which processors are mostly used in the network, right? Again, obviously it is the Zoom that is number one, because that is what is getting transmitted to you guys, and GPU, and not only that, even the power also. Okay, you can see the power consumption is the highest is Zoom, right? Highest is Zoom. So likewise, you can look at which processes are taking more of resources, and one process may be taking a lot of this resource but not that resource, maybe a lot of memory access but not much network access, or not much disk access. Okay, right? So CPU bound means those processors need a lot of processing power, right? Take a lot of processing, but IO bound means they need less processing. They are more idle, right? More idle because frequently it's waiting for user interactions, right? So another classification is independent processors versus cooperative processors. So independent processors means these say we have process 1 and process 2. So they have no common things. They are not interacting with each other. They are independently running. So we call them independent processors. For example, I am having my WhatsApp, right? WhatsApp, and I am having my Notepad++. So they are definitely independent. So they have nothing to do with common things. Okay, but my my Chrome, my Edge browser is running. So inside that, some PDF reader is also running. Then that PDF reader and my Edge browser are sort of a cooperative process because that PDF reader is running inside the Edge browser. So if they are highly cooperating, we say they are cooperative processors. Okay. Right. So now last time I told you that this overall thing is done by what is known as process scheduler of the operating system. Right? Process scheduler. Process scheduler is just a subprogram in the operating system. But if you want, we can subdivide that process scheduler into 3 sub-schedulers. And we call them long-term scheduler, short-term scheduler, and mid-term scheduler. So this is not directly mentioned in your syllabus, but it's always good to know this because examiner is also running out of questions sometimes. Okay, he can't ask the same question every year, so then he will just go a little bit beyond your syllabus. So this is one area he may touch, right? So yes, overall we say that is done by the scheduler, but we can subdivide it into 3 sub-schedulers. The long-term scheduler is the one that admit or decide whether a program is ready to take from new to, is it ready to take from new to ready state? So that is called long-term scheduler. The short-term scheduler is the one that handles ready to running and running to ready transitions. So that is short-term scheduler. Okay, so the medium-term scheduler is the one that decides on whether you put it into the block state and also taking back to the the medium scheduler is the one mainly thinking about or the considering whether to put it into suspended or not and put it to suspend or take from suspended to ready or whatever, right? So that is medium term scheduler. So if you look at this diagram, sorry, delete everything. Now we are pretty much done with the process scheduling. So this is the best place to write down, right? You can even write on your PDF. Okay, so you can open your PDF in the Edge browser. So you can take this drawer and you can take your notes. Okay, even with mouse, it will take a little bit time, but still you can do it. So you don't have to take printouts. You are IT students. You are not grade 6 students, right? So this is done by long-term scheduler. Okay, so this one, and this is done by short-term scheduler. Okay, so whether to put it into suspended or not. So this part is pretty much under medium-term schedule. Okay, medium-term schedule. So this is also more into the short term. Okay, this one also, but the virtual memory handling part is pretty much medium-term scheduler stars. Okay, long-term scheduler, short-term scheduler, medium scheduler, but we just feel it like one schedule. Okay, right? So that's it. That's it on process. Okay, so we have two more subtopic. Okay, So sorry, we have two more subtopic. Now remember, I told you that why they are moving from ready to running, running to ready, ready to running, running to ready. Why? Because the processor want to give each process a fair chance of running. Right? Otherwise, if one program runs to the end, the user will feel like other programs are not responding. Right? So that is not what we need. Right? For example, say you are doing something. Right? You are doing something and someone asks you a question. Now, which one is the nice thing? Say your task take another 10 minutes. Are you going to do the 10-minute task and then answer that question, or just give that person attention and again come back to your task, and once in a while give the attention to the other person also? Or are you going to say that no, just wait, I will finish this and I will talk to you? Right? That is not what usually we expect, right? So therefore it is for our benefit, because overall that we are happier, because we feel like everything is happening. Okay, right? But this can be done in two different ways. Right? So what is mean by this? Putting it to running and taking back to the take it back to the ready state, right? So there are two ways or two mechanisms or two strategies we can use. So we call them preemptive context switching and non-preemptive context switching. So this is very important. It's extremely important for your exam. So preemptive context switching means when we are sending a process to the process from ready to running, we are only giving it a fixed time slot, say 10 nanosecond or 10 millisecond. Actually 10 millisecond is too way bigger, right? Practically it is in just little less than 1 millisecond. Right? So whenever a process is taken to running, it is given a fixed time slot. When the fixed time slot is over, it has to always go back to the ready state and wait again, it get a chance. So then we call it preemptive context switching, right? So fixed time slices are received. But that time slice can be different. Maybe X is getting little bit bigger time slice, Y is getting a smaller time slice, but you are getting a fixed time slice. After the end of that time slice, you will be taken back to the ready, so that some other process is given chance. Right? So then someone will ask why some processors get bigger time slices and others getting lesser. So it depends on two things. One thing is your operating system decides if one program need lot of processing, it will be given little bit more attention, because otherwise it will be delayed. The second one is you also can control. There's something called priority, right? So usually we don't go and change it usually, but if you are configuring a server or something like a software engineer, so then you will do that kind of things, right? So again, I'm going back to the task manager. So there's something called here, there are some services, etc. Okay. Okay, so you have to go to the details, right? Okay. For example, say I want to give my Zoom higher priority. You have to go to the go to details. So then you have that, you can see sub processes are there. Right click and there's something called set priority. So it is by default, it will be normal priority, but if you feel like it is slower, right, and we need to make it a little bit faster, you can just increase the priority. So that means we also have a bit of control, and operating system is also not giving every process the same amount of attention. It also decides which one need a little bit more attention, etc. Okay, right. Anyway, so still your processors are going to get fixed time slots if it is preemptive, right? Preemptive. Any questions on that? Right. So then the non-preemptive context switching means when a process is given that process attention. That means when a process is taken to the running state from the ready state. So it will be given a chance to run until it gets terminated, or it's done. So when something is given a chance, of course, it has to wait until it get a chance. But once you get a chance, your processor is going to let you run for until it is terminated. Or it reached to a waiting state. So waiting state means you need input output, use attention. Of course, if it is use attention is needed, it's a waste of resources to let you running, right? Because you can't run now. You are waiting and you are just in the running state, and others who are genuinely need has something to do is in the ready state. So therefore, there are two possibilities. When you, if it is non-preemptive, if a process is taken to the running, either it will be allowed to finish it, or if it reach to a block state, that is use attention state, input output state, then only it will be taken back to the that particular block state. And of course, that use attention is done, it will be getting back to the ready state. And now again, it will be when it's taken to the running state, unless there is any use attention, it will be allowed to do until finish. So that is called non-preemptive. Okay, non-preemptive. But usually computers are mostly preemptive, right? Mostly preemptive because that is more democratic, right? Every program is given a fair share. So then someone will ask, yeah, in general, computers are preemptive, right? But there are special cases where the computers can be non-preemptive. So that is, I told you that when we subdivide operating systems, I told you we can subdivide it to single user, single task, right? Single user, multitask, multi-user, multitask. Okay. And can anyone remember another thing? Can anyone? Single user, single task, single user, multitask. Sorry?
Real time?
Yes, real-time operating system. So what is mean by real-time operating system? So we try to do things in real time. So when there are critical operations like defense, missile guiding systems, right, life supporting systems in health, so we have split of a second to decide and finish it, right? Just a split of a second, we have to act and finish it. So in that kind of operating systems, they mostly use non-preemptive, because when they get that process to run, you can't just go to running, waiting, and do it. These are super critical tasks, right? So therefore, that kind of tasks, when there's a need to do that, they must be put it into the running state and let it finish, because otherwise it is too late. Okay, so especially non-preemptive context switching is used in real-time operating systems. Okay, but I'm not saying that it is not done in normal things, right? But mostly it is for the real-time operating system. Okay, right. So this is our final subtopic related to the processing, right? Operating system level, process control block. PCB. I think I discussed about file control block when we were doing file. I think I may did it. I may have done it, or maybe I forgot it. Okay. So there's something called file control block. So when you are just right click a file and say properties, you are looking at that file control block in a little bit user friendly manner. Not entire file control block, just some part of the file control block. Okay, so what is file control block? It gives you the overview of the property of the big picture of the file. So it's not rocket science, it's very simple, right? So what is the file name? What is the extension? Whether it's a zip file or PDF file or exe file? What is the file size? So these are the things that we can see, right? So then the operating system keep track of few other things also. If it is a open file, that is you have been using it. What is the record length? How many? Which record now we are in? If it is being processed by uh, program, so those things we are going to do when we are doing the Python. So you have a topic called file handling. So using your Python program, you can read records by records. So then at any time, your operating system must know, we read last time, we read the say 20th record. So therefore, next time we are supposed to read 21st. So those kind of things are also there in the file control block. File record length, record number, right? The last modified date time, of course, that is, you can file it in your properties also. So this is in general called file control block, FCB. So in the exams, they have asked it, I think, very recently also. What is mean by file control block? What are the properties available, etc. Right. So now this is, of course, this is not related to file control block. Just the name looks similar. That is why I just reminded it. There's another one called, another concept in operating system called process control block. That is FCB. This is PCB. So PCB is, now remember, the process operating system has to take processes from ready to running, running to ready, ready to running, running to ready, and of course it can go into some other state as well, right? Suspended, right? Blocked, etc. So therefore, whenever there's a state transition, maybe going from ready to running or running to ready or running to the blocked or blocked to the ready or blocked to the suspended or whatever, whenever there's a transition, it accesses the process control block and it write the current situation or things related to the current situation, current state in the process control block, right? Which is not visible to us, which is something your operating system keep track of in the memory. Okay. So say when a process is taken from running state to the ready state, it is going to update the process state saying now it is in the ready state. Right. So when it is again taken to the running state, it is going to update it saying, okay, now it is in the running state. Right. So then every process is given a number, right? PID. So always look at these things in practice, okay? Don't just memorize, it's boring and so many other things, right? So your processors have the process IDs, PIDs. Maybe if you look at the process properties, you will be able to see it, or you have to go to the details. Right, so you can see PID. Okay, so different IDs, 16,440, 824, and blah blah blah. Different processors have different IDs. So your operating system must know what is the process IDs, right, or the process number is, right? So that is also there, right? Process status, process state, whether it's now in running or suspended or blocked, and what is the process number, because operating system refer to it using the number rather than naming it like Firefox or so. Then program counter is, now remember the process is a running program. Program is having code. So program counter is what is the last execute statement number, because your program is in the memory. In different memory addresses, what is the address of the memory that you last execute your program or process? That is called program counter. So why it is important? Of course, it is important because when, say, now it is in the ready state. Now, when it is taken back to the running state, it has to read this program counter and load the next instruction, because you have to execute from that point onwards. You don't have to execute it from the beginning again. So now you know that why program counter is important, because it says what is the current last executed statement. So therefore, next you have to take that next program statement. So then it keeps track of the registry values. So why it is keeping track of the registry values? Now remember, when a program is executed, it takes instructions one by one to the processor and execute. Then the next instruction, and also when an instruction is executed, if there are relevant data, it has to load to the registries. Right? Registries. So registries has the data. Now remember, while your program is running, in the middle, operating system decide you to take you back to the ready state again, because your time slot is over, especially if it is preemptive. Now, all of a sudden, when you are taken back to the ready state, your registries may be having some data. Still, you have not written it back to the memory. So therefore, whenever it has a process transition, it take a copy of the registry values also, because next time when it is given the attention or running state, it has to not only look at the program count and see from which line we have to execute. It has to load the or reinitialize the processor registries with these values. So then only it is ready to go from that point onwards. So that is why it is keeping the registries. Right. Okay. So memory limits, you don't have to worry too much. That is every program is referring to its. It must know what is my where is in which memory addresses the program is, in which memory area the relevant data is. So those things also it has to keep track of, because next time when you are given running slot, time slot, you must know from where to access. And also the list of open files, because if your program is working with files, and all of a sudden when it is taken back from running to the ready state, you must know which files I have been working with and which record I last accessed, because if it is reading a file, next you have to read it from that point onwards. Now remember, that is why the file control block keep track of what is the current file record. Now you can see the file control block will be consulted by your process control block to find out what is the last read record, and it is kept in the PCB as well. Now you can see why there are so many fields, because of this going to running and coming back to ready and blah blah blah. Next time when it goes to the running, it needs these fields to do it properly, continue from where it stopped. Right? It needs the program counter, it needs the registries, right? The memory limits, the file open file list, etc. Okay, so never memorize what PCB is this and this as that and this fields. No, right? That is headache, right? So that is not going to work. So of course you have to remember, but remember, while you know why these fields are, then actually you don't have to memorize. You will naturally remember it. Okay. Because if you just memorize, when exam is nearing, you are going to feel the pressure. And sometimes you may get blank also. But if you understand it, that never happens. Okay. Right. Now I hope you know what is process control block and why we have these things. And this is again something operating system maintains for all the running processes, currently running processes. Of course, when a program is terminated, the operating system no longer required to keep track of that PCB, okay, because that program is terminated. But all the running programs has a one PCB. Right. I explained this at the beginning, right? Multiprocessor versus single processor, and what is mean by multi-core, right? Same chip, but more than one physical processors, dual core, octa-core. Then the logical processors also, right? It's not physically processor, but operating system may look at a one processor or one core as maybe 2 or 4 logical processors as well. Okay. Right. So any questions? So now we are into the final part of the operating system, right? Memory management. Any questions? No. Right, we'll take 5 minutes break. Now it is 4:42. We'll be starting at 4:47. And we will finish the memory management. And it's a very important part. That is the most difficult part according to students. Okay. And therefore, examiner is really interested in giving questions on this because it is very challenging for the students. Okay. So we'll continue. Right. So memory management. Right. So when it comes to memory, we discuss about the memory in the hardware side also. Okay. So memory, we can look at memory as something like this. So memory, we have memory address, and each address can keep your content or data. When I say data, it can be data or program. Okay. Because memory is memory. And I told you that most of the your memory is filled with programs, but we just say that data memory can keep data, but actually it's content or whatever. Okay, but anyway, so so we have the memory addresses, and each address can keep set of data, and of course address is also binary number. Your data or your program statements are also binary number, and this is the unit that we can access from the processor. So processor can say, I need to access this particular memory or content of this particular memory address. So that is the smallest. That is the smallest. And always processor access your data or memory using the memory addresses. Okay. So that is why we have, remember the processor side. And this is our memory or RAM. There's a system bus. So that is the most important bus. So bus in computing is the data, the communication parts. So this system bus has 3 components. What are those 3 components? The data bus, address bus, and control bus. So again, when we say data, data means again content. Okay. Content. So the data bus is used to send and receive data. Address bus is used to send and receive these memory addresses. And of course, the control bus is used to send control signals, because we have to say, I need to read the data. No, I need, I'm just, we are now interested in writing this particular data and see some other things. So therefore, this memory address is extremely important concept, because that is how the processor look at the or access the memory. Okay, right. So there are 2 approaches, byte addressable and word addressable. So byte addressable means every byte of data has a memory address. Word addressable means maybe every 2 byte has a 1 memory address can keep 2 byte of data or 4 byte of data. If it is more than byte, we say it's word addressable. That I hope you can understand. Okay. So then there was another concept called byte ordering or endianness. Remember, we discussed that little endian versus big endian. So if your data is too big for one memory location, that often happen. So then you have to break it into maybe 2 or 3. And this portion goes to this one, this portion goes to that one, and this portion goes to the next location. So usually consecutive locations are used. So you can do it in 2 ways. Maybe your left hand is given the lower value, then this one, and then this one. Or else this goes to the lower value, then this, and then this. So depending on whether you go from left to right or right to left, we call it little endian or big endian. So little endian means the least significant is the right hand side. So remember when I said to 3,578, this is the least significant. This is just 8, but this is 3,000. So least significant part is this one. If the least significant part is given the small address, then the next one, we call it little endian. If more significant part is given the low address, then the next one, we call it big endian. Right? Right. So byte addressable versus word addressable, little endian versus big endian. Okay, those are additional things. Okay, right. So what we are interested more is some other thing. Okay, there's another concept also, because these things they can ask separate questions, right, in the MCQs. Right. I will explain you the main thing later. That is in your structured paper. Okay, still I'm setting up some additional or background concepts. There's another concept called memory segments. So when you take your memory, computer memory, RAM, right? Say I have 8 GB of memory. The moment your operating system is boot up, it mark up regions in the memory. It's a soft thing. It's not a hardware level thing, hard thing, right? So it mark this memory address range is for this purpose. That memory address range is for this and this, and likewise it logically separate your, if it is 8 GB, your 8 GB, if it is 4 GB, your 4 GB into separate parts, and we call them memory segments. Right? So obviously one portion, one range of, actually two range of memory addresses are reserved for operating system load, because first of all it has load to the memory as well, and most of your memory is taken by your OS actually, nothing else. If it is 8 GB, maybe about 3 GB of the memory is occupied by your operating system. So that is OS segment. Usually you have two OS segments, okay, because it's huge. So then the programs are loaded to the text segment. Right? For example, right now the Edge program is running, Zoom program is running, right? And some other WhatsApp client is running. So those programs, remember the memory has both programs and data. We say that they are loaded to the text area, and different programs are given different ranges. They are also not mixed. And data related to those programs will be in the data segment. Like if it is a web browser, the web pages. So then there we have the stack segment. That is when you are doing some processing, sometimes you have to put it back to the stack and take it back and blah, blah, blah. And method calls, stacking, etc. And all the rest of the memory is called the heap. So that is the global or the free area. Right? So that is why when you take the task manager, so it says this much of memory is there used, this much of memory is available. Right? So you can see I have 8 GB and right now 2 GB is available. 6 GB is used. And this 6 GB is your OS segment, text segment, and blah, blah, blah. Okay. So if you need a little bit more details about this, you can go to the process. There's a link called process monitor. Okay. So you have to go and look at those things. Okay. So there you will see little bit more details, right, about CPU, memory. Okay. Free, standby, right, modified, in use, blah, blah, blah. Okay. And CPU side also you have a little bit more details, services, etc. Okay. And you can see more details there. Right. So now you know that there are memory segments also. And of course, the concept called byte addressable and endianness. Right. Now, this is the most important part that we are going to, that is needed for the exam from this point onwards. Now, from this point onwards, discussion don't mix with whatever I explained you previously, like byte ordering, the endianness, right? Byte versus word, memory segments. Those are additional things. But this is what we need to understand in order to do your structured paper question. Okay. So that is, I told you that there's a concept called virtual memory. Why do we have a concept called virtual memory? If our physical memory is not enough, your operating system can take part of your secondary storage, that is your SSD or hard disk, as an extension to the memory, right? As an extension to the memory. So it's not real memory. It looks like, or it's just think like memory, but it's not real memory. So therefore we just call it virtual memory. Okay. But there's more than that. More than that. It is not just temporary area, we use it and later take it to the main memory. No, it is more than that. There's a little bit more story behind that. What is that? Right. So listen to this very carefully. So we have physical memory. So what is physical memory? Your real hardware memory, not something shared from your hard disk or SSD, right? Your real hardware memory. For example, in my case, my computer is having 8 GB of physical memory. Okay, so that is called physical memory. Right? It depends on your memory chip. Maybe one person have 4 GB, another person 8 GB, another laptop is having 12 GB, even 16 GB or 32 GB. So that is called what? Physical memory. Okay. And that is the reality. That is a reality. That is a real memory. So then we have another conceptual memory. Right? That operating system think like it's a memory. Right? So we call it either logical memory or virtual memory. But here it is different. Now, the confusion is, lot of students' confusion is, we use the word virtual memory for two different meanings. Now, one meaning is, I already explained you. You have the real memory, then we can borrow part from your secondary storage, and we call this virtual memory. Right? We call this virtual memory because this is not real memory. So that is the meaning one, because the same word may have different people use it for different meanings. Unfortunately, ideally we should have for two different things, two words. But unfortunately, right. So this is one meaning of virtual memory, that you borrow from your secondary storage or the hard disk or SSD is called virtual memory. Okay. So the second meaning is, the operating system look at memory, your real memory as physical memory, and this virtual memory plus your logical memory or your physical memory together as logical memory. Got it? So this is your physical memory, actual memory. We call it physical memory. Then you have your physical memory plus that extend from the secondary storage, that is virtual memory, and we call that together as logical memory. Okay. Right. So then you will say, okay, that is fine. I'm not confused at all. There's no confusion. That is clear cut. Yes. This is the confusion. Sometimes, not sometimes, most of the time, this logical memory is also called virtual memory. So that means sometimes people call, when we say virtual memory, we are only referring to this part. But in other times, when we say virtual memory, we are referring to this big thing. Or we are using the word virtual memory as a synonym for logical memory also. Okay. So you have to keep it in mind. Especially if it is a memory address translation question, when they say virtual memory, you just replace the word with logical memory. So when they say virtual memory, you just mean it as the logical memory, the memory that operating system see as a logic. Okay. I told you that a lot of students find this is the most difficult part in your ICT exam syllabus. So the main reason is they get confused. because it is used in two different ways. This one, or sometimes instead of logical memory, we just say virtual memory. So therefore, just remember that in your memory address translation question, if they say virtual memory, you just consider it as a logical memory. The memory that your operating system see it as a logic. Okay. I hope it is now clear. Okay. So then someone will ask, why does your operating system want to see this as a logical memory? Why can't your operating system only looking at your physical memory? So the main reason is physical memory is most of the time not enough. Not enough. Because so many programs are running. So therefore, almost all the time, it relies on this extension from the secondary storage. Okay. So therefore, here we have set of memory addresses and content, but that is most of the time not enough for your running programs, because there are so many programs running, and sometimes not entire program is loaded to memory. Sometimes what happens is only part of the program is loaded to memory, and when needed, later the other part is loaded. Okay, so therefore operating system need to look at it as a bigger thing. Otherwise, it can't handle the execution. So therefore, your programs look at your memory as this logical memory. This logical memory. Okay. But in reality, this is the memory. This is the memory. Of course, this part your processor cannot access directly because this is in the secondary storage. Okay. So this is, you need to ask questions and clarify if you need any more clarification. Okay. Right. So I hope you got it. Right. So why there's a concept called logical memory? Because there are so many programs. So programs need to look at it as a bigger chunk, because it is actually it is not enough most of the time. So that is why we have a concept called logical memory, or sometimes we call this logical memory as virtual memory. Okay. But some other times only this part is considered as virtual memory. When we refer to virtual memory for the logical memory means actually the physical memory plus that additional area we take from secondary storage. Okay. And also every program is going to look at your memory as one particular virtual memory. So that is another important thing. Say if you are running 3 programs, currently there are 3 processors running. 3 processors running. Each process is going to look at its own virtual memory. Its own virtual memory. But in reality, all these are in the physical memory, and additional things are in the secondary storage under that, the real virtual memory. Okay. So each program is going to see its own logical low virtual memory. Again, better word is logical memory, because right, otherwise we get confused. Every program is going to look at its own logical memory, and in reality, part of it will be in the physical memory and other part will be in the secondary storage. Or in some cases, entire thing is in the physical memory, if it is 100% in the memory. Okay. So therefore, your programs always refer to this logical memory address. So that is very important. Right. So I told you that when you write a program, we have to compile it, or we have to translate it to something closer to the machine code. Then that it is not machine code. It is what we call it assembly code, somewhat closer to the machine code. Then it has to be converted to the machine code in the processor. So that machine code and the assembly code refer to memory. When it refer to memory, it refer to it's that imaginary or logical memory addresses. But in reality, there is no such data. So therefore, there must be a mechanism to translate that logical address into the physical address, because it is ultimately the physical memory you have to access. Okay, so that is what we are supposed to do. We have to convert the logical address into the physical address, because that is where, because the program is referring to the logical address, whereas in reality it has to be taken from the physical address. Okay, so that is what is known as memory address translation. It's a long story, and I just gave you some idea only. Some more concepts you have to understand in order to do this. Okay, and the other thing is the physical memory, and I told you that the operating system, we can look at it as different sub programs, right? So I told you that we can consider the sub program that doing the process state transition as the scheduler, and that scheduler we can consider it as 3 sub schedulers, right? Short term scheduler, mid term scheduler, and long term scheduler. So similarly, the part of the operating system that do this memory address translation from logical memory address to the physical memory address is called memory management unit, MMU, right? You can see there's a thread scheduler, there's a memory management unit, right? So the memory management unit is the one that is doing these translations in the operating system. And this is extremely important, because every time your processor want to access a particular data or program statement in the memory, because your program is referring to the logical memory address, always it has to be translated to the physical memory address, and then that physical memory address will be sent by the address bus to the memory, and the memory is going to send that data or instruction through the data bus. Or if it is writing, your program is saying that write this data into this particular logical memory, then the operating system has to convert it to the physical memory address, and it is going to write it into that particular physical memory address or data location in that particular address. Okay. So anything that you want to clarify? I told you that most of the students consider this part as the most difficult part in A-level ICT. I'm not saying that it is difficult, but you have to think about it. You have to consider all those factors, unless otherwise you will not be able to answer the questions. Because examiner is also asking some tricky questions to check whether you have understood it fully. Right. I told you that the smallest unit that your processor can access is data related to a memory address. Right? Data related to memory address. But at the same time, your operating system, right? Your operating system have another unit in both physical memory and logical memory. So that means your operating system divide your physical memory into portions, right? And we call it frames. Frame 1, frame 2, frame 3, etc. Right? Physical memory is subdivided into memory frames. So each frames may be having set of addresses, and of course each address you can keep data, right? Maybe one memory address can keep only 1 byte. Maybe one frame is 100 byte to 1024 byte to kilobyte, 1 kilobyte. Okay, that is 1024 memory locations if it is 1 byte each, and we call them frames. Okay, that is the physical memory side. In logical memory side, that is what your programs are referring to. It look at memory as something like that. So they also subdivide it into portions, and there we call it pages. Page 1, page 2, page 3, etc. Okay. So logical memory is subdivided into pages. Physical memory is subdivided into frames. Okay. Then there's another very important thing related to this page and frame. That is the page size is always equal to frame size. So this is something you have to remember, okay? Or you can just take it a note as also. What is the most important thing when you are doing these questions? Page size is equal to frame size. So if the page size is 1 kilobyte, one frame is also 1 kilobyte. It's never different. Okay. Why it is so? These pages will be fit into a frame. Maybe this page 1 is in the frame 2. Page 2 is in the frame 1. So therefore, always the page size must be same as frame size. Okay, so remember this is the program, a particular program's view of the memory. Every program look at the memory as this consists of set of pages. An operating system is also looking at like that when it is executing program. Okay, and this page size is same as frame size. And at any time, right, your operating system can map a page to a frame. Now, operating system knows that this program's page 1 is in my frame 2. Of course, different programs may be having different pages, but there are only one set of frames because one physical memory, but multiple logical memory because different program is one particular program's view is one logical memory. Another program's view is its logical memory. Okay. So these pages will fit into a frame. Okay. So sometimes what will happen is the memory is not enough. Right? Memory is not, physical memory is not enough to put up or fix that. Say I have this program has 3 pages, but there's only one frame left. Maybe one of the frame is used by this. One of the pages used, put it into a frame. Now these 2 pages, you don't have enough time in the physical memory. Then these pages will be taken to the virtual memory. Okay, because it must be somewhere. So now some pages are in the map to a frame. The particular page, every page must be have a one-to-one mapping. That mapping is either page to a frame or it is page to a virtual memory. It's also sort of a frame, but we say that it is not in the, or we say that it is not mapping to a frame actually, because frames are in the physical memory. We just say that it is in the virtual memory. It must be in the virtual memory. There's nothing called, it's in some of the pages are in the physical memory and other pages are nowhere. No, if it is not in the physical memory, it must be in the virtual memory. Okay. Right. So then operating system has to keep track of which page is in which frame, or is it in virtual memory. So that is done by your memory management unit. Remember MMU, by keeping track of something called page table. Something called page table. So the page table is the one that your operating system used to, or your memory management unit used to keep track of which page is mapped to which frame. Now you can see that this is the page table. So it says page 0 is mapped to frame 1. So therefore page 0 must be here. Yes. Page 1 is mapped to frame 4. So therefore page 1 is in the frame 4. Page 2 is mapped to frame 3. Yes, it is in the frame 3. So these are the frame 0, frame 1. Usually we count from 0, okay? And this says page 3 is mapped to frame 7. Yes, so that means all the pages are in the physical memory. None of the pages is in the virtual memory because we have enough memory here. So this is called the page table. This is a page table. Got it? If you feel like, no, I lost it, immediately you have to say that, no, I was able to understand up to that point, but just now I lost it. So you have to just interrupt me and ask me to explain it again. Okay, I can explain it any times, because I told you that the students consider this as the most difficult part. Okay, so then why should I bother, right? Of course I have to bother about it, right? I can explain it 100 times if you need, right? Then I told you that, of course, this is a happy scenario where every page is mapped to a particular frame, but there can be a situation where your physical memory is running out of space, right? Running out of space. In that case, what it does is it has to put that page into the virtual memory or the disk space, like disk space. So in that case, how do you know that it is not mapped to a particular frame? So that is where your page table has another field. Now remember, your page table has, so a page table had two fields: page number, frame number. Page 0 is mapped to frame 1, page 1 is mapped to frame 4. Right? So now we are going to introduce another field: page number, frame number, valid bit. Valid bit. Right? Or valid invalid bit or whatever. Okay, valid bit or valid invalid bit. If a page is mapped to a frame, the valid bit is going to be valid or true. You can see page 0 is mapped to frame 4. So therefore, this page 0 is considered as A is in frame 4. But page 1, you can see it is invalid. Invalid means your page 1, we denote it like capital B, is not in the physical memory. That is what it means. If it is not in the physical memory, it must be in the disk storage or the virtual memory. You can see that B is here. B is here. So see, it says, so the 2, page number 2, it says it's in the 6th frame and it's valid. Yes, it's in the 6th frame and it is valid. 3, it says invalid. So therefore D must be somewhere here. Right. So 4, it's say invalid. So therefore E must be somewhere here. 5, it says valid and it is in the 9th frame. Yes. Right. And 6, it's a invalid. So G must be here. So this is not, this one has not shown in all the things actually. Okay. So G must be somewhere here actually. Okay. H must be somewhere here because they are all invalid. Okay. They are all invalid. And this is small mistake. A must not be here actually. A must be here. Okay. So this diagram also has small issue. Okay. Because A is here. When it is here, you don't have to keep it here. Okay. Right. So that is how, if it is invalid, it must be here. If it is valid, this is the frame number. Right. This is the frame number. That is how you look at it. I hope you can understand up to that point also. Okay. Yeah. So that is exactly right. So that is good that you pick it. Right. So that is a mistake. Right. Actually, this is not some diagram. I draw it. I took it from some other book. Okay. But there's always that possibility also. Usually when you take it from here to here, sometimes you don't delete it as well. Sometimes it will be deleted later. But as long as it says it is valid, we don't look for this. We don't look for this. Because we know that the latest or the updated one is in the physical memory. But usually this is not something, it is not supposed to be here also. It will be deleted when it is taken to the memory. Usually it is deleted, but maybe a little bit later as a background process. Okay, right. But anyway, you can just consider this is not there, or though it is there, we don't care because your table says it is already in the memory. Right. So that is how it works. So therefore, you have to look for the valid invalid bit as well. Okay, valid invalid bit as well. Right. Now we are into our final part, that is how to do the address translation. And another thing I want to mention, right? Usually, and in A-level ICT, it is always, almost all the time, right? But if not, examiner will tell you, usually the physical address is size is 1 byte. 1 byte. But just keep it as in the mind, but usually you don't have to rely on that. Right. And also there can be special cases where it is not 1 byte, but in the MCQ or something, if they ask what is the size of the physical memory, and if they have not provided any other information, yes, default physical memory address is 1 byte. Physical memory address is 1 byte width, that is 8-bit width. Okay. Right. So that is a special case. Okay, special case. But again, that is not a rule, but in general, it's 1 byte. But logical addresses can be anything, right? It's usually bigger than 1 byte. I told you that the logical address space or the size is bigger than the physical address space or the physical address size. Okay. Right. Now we are into the most important part: how to translate your logical address into physical address. Okay. How to translate your when you are given a physical address, sorry, logical address, say something like this. How do you find the physical memory address using the memory page table? You have only the page table to do that. Right. So this is how it is done. Now this is the final set of things. If you understand this one also, yeah, then you are done. You will be able to do the page translation. Okay. Memory address translation. Right. So your logical address, because we are going to translate the logical address, which is set of bits, right? It's a binary number, into a physical address. Why? Because then we have to go and access it and give it to the processor. Your logical address has 2 portions, right? And your physical address is also have 2 portions. So we be doing something like this. So I will say the second most difficult part that the student says, right, is subnetting. There's a networking subject, you have something called subnetting. So the student says the second most difficult part for the A-level ICT is understanding subnetting. So there also IP address is divided into 3 portions. So I don't know why when a number is divided into portions, students find it difficult, right? I don't know. It's a funny thing, right? Right. Anyway, forget about that. That we'll be discussing when you are doing the networking. But because there's a lot of logic behind that. Okay. Right. So what is the thing you have to remember? Your physical address is subdivided into 2 portions. Your logical address is subdivided into 2 portions. Okay. And this is your page number. Right. This is your, in the logical address side, the first portion part is your page number. And in the physical address, the first part or the left part is your frame number. So that means page number to frame number, we have to find out what is the frame number is, because we have to find out this. So that means there must be way, when you are given the page number, we must find out what is the frame number, because in the physical address, the first part is the frame number. And that is exactly where we use the page address page table, because page table has the page number to frame number mapping. So it says page number 2 is in frame number 5. So therefore we use the page table to find the frame number. How to find the page frame number? We just check what is this page number, and for that page number, what is the frame number. If it is page number 5, and if says, right, it is frame number 3, now you know that it is 3. 5 mapped to 3, of course, in binary. Okay. And again, you have to look at the valid invalid bit also. Actually, first you have to check the valid invalid bit. If your page number 5 says there's no frame number, it is invalid. That means you can't map it. There's no physical address because it is in virtual memory. So that is the first thing you have to look at. Right? You go to the page table and go to the relevant page number and check whether what is the valid invalid bit. If the valid invalid bit says invalid, that's the end of the story because it is not in the physical memory. Invalid means it is in the virtual memory. So then you don't have to do a translation. You just have to say it is not there. Of course, there's another thing to do in that kind of situation, which I will be explaining later. But you can't do a translation because it is not there. It is invalid. But if it is valid, your page table will have the frame number that you have to take it there in binary. So now you have the left portion of the physical address. Then what about the right portion? That is very easy. You just copy the right-hand portion of your logical address to the right-hand portion of the physical address. Then your physical address is there. Now you got the physical address. Only if the valid invalid bit says valid, and this has a valid number. So you replace page number with frame number and copy the right-hand portion from here to here, and you got the you get the physical address. Got it? Right. So then someone will say, okay, I can understand that this page table is giving you the mapping. So therefore, you are replacing page number with frame number. Then why you are copying this portion as it is? That is a good question, right? If you have done this topic in your school or any other place, right? So I don't mind, right? I don't mind. Right? I am really happy if you know it. I don't mind from where you learn it, as long as you learn it, right? So therefore, don't hesitate to answer. If you have learned this, right? I'm really happy about that. Okay, if you have learned this or if you have studied this by your own or whatever in school or whatever, can someone tell me if you have done this only? Otherwise, you may not be able to answer this. Why this portion is copied to this portion as it is? I told you the most important thing is why, and I'm going to explain it. But I like to know if you know it, if you have done OS part in your school or whatever. Just you can explain it in one word. If you give me that word, I know that you know the subject. So maybe still you have not done this portion, huh? Maybe. Right. So the reason is this part is called the offset. And of course, this part is also the offset. So offset means, now remember your data is in a particular page. In that page, now different pages have page numbers, page 0, page 1, etc. So the first portion is the page number, right? The second portion is in this particular page, which say whether is it the 10th data or 11th address or 12th address, or right? Because assume that there are 1024 entries. So the second portion says, okay, in this page, or okay, whether is it 10th location or 11th location or 12th location or whatever. If it is 10 here, 11th here, 12th here, likewise say 1024 locations. So that is called offset. If it is in the second, if it is that is in the frame 0, page 0, if it is page 1 also, it starts from here, right? Because that is the page 1 now. Maybe this is your 5th data. 5th data is you are referring to. So therefore, this is the offset. This page, this offset. Now I told you that page size and frame size is the same because the page is going to land in a frame. So therefore, when a page is landed in a frame, this offset is not going to be changed because the data is going to be just copied here. If it is the 10th offset here in the page, it has to be the 10th offset data in the frame as well. So therefore, we just can copy this portion to this portion. Only thing is, rather than the page number, we have the frame number. Okay. So that is why we just copy the right-hand portion from the logical address to the physical address. Okay. I hope you got it, because otherwise you don't know why it is happening like that, right? So then you are just memorizing when you are stressful, right? You are really stressed because you are memorizing something you don't know. Right. Right. Now we are done. Now we are done. Okay. Now we are done. And usually, not usually, all the time, your logical address will be bigger, physical address will be smaller. Okay. Because we have less number of frames than number of pages. Right? Because I told you that your program look at it as a logical, that size plus virtual memory size. So therefore, obviously there are more pages. So when you have more pages, you need more bits. Say 1024 pages, say 32 pages, but 16 frames. Then of course, your page number is going to need more bits. This one is needing less bits. So therefore, always your logical address is bigger, physical address is smaller, but though it is smaller, this part is the same bit because that is the offset. Only thing is the page number is bigger, frame number is smaller number, relatively smaller number, because we have relatively smaller number of frames. Okay. So likewise, everything you must be able to understand and explain. So the best thing is, if you have a student, if you have a friend and he or she says, no, I haven't understood this, I'm really upset. So you go and explain to her or him. So that is, then if he or she says, okay, I got it, I don't have any questions now. So now it's good for you also. It's good for you because you help someone. At the same time, your confidence is also high. Okay. Okay. Right. Now the examiner can give so many different questions for you in this area. Okay. In this particular area. Because this is something interesting area as well. Okay. Right. Now let's take an example, practical example. Okay. Say this is my logical address. Assume that this is my logical address. Now I want to find out what is the physical address is. Now in the question they have to give you where this margin separation is. Otherwise you can't do it. Right. So the examiner is going to tell you that your logical address is separated in somewhere here, or here, or there, or whatever. Now assume that it is separated here. Now that means this is the page number. This is the offset. Now this page number is, now let's convert it to decimal. 0010 is what? 2. Assume that here we have the either here also you can have binary, or maybe they can convert it to decimal. Assume they have converted decimal. Now we know that 0010, or they can just say 0010, or they can just say 2. Right? So 0011 is 3. So now you can see this is 0010, that is 2. Therefore, you have to go to the second row entry. And second entry says valid invalid bit is 1. So 1 means valid. 1 means what? Valid. So that means it is in the physical memory. So therefore, your page number is this. So therefore, it is 110. I told you that usually the page number is smaller. If this take 4 bit, it takes 3 or 2 bits. Right? So therefore, 0010 is going to be replaced by 110. Right? 110. Now we got this portion. Okay. So then this portion is the offset. And in this case, this says 0, 1, 2, sorry, 1, 2, 4. It says this is the fourth record in that page. If it is the fourth record in the page, in the frame also, it is going to be the fourth record. So therefore, we just have to copy this portion, right? Copy this portion. So you just have to copy this portion and we are done. For this logical address, this is the physical address. This is the physical address. You can see that it is not rocket science. Huh? It is not rocket science. And it is just a simple logic that A-level student should be able to understand. Okay. Okay. So that is how you do the translation in reality. Of course, if it is something like, say, assume that you got this 1, 1, 1, 0. 1, 1, 0 means what? 1, 2, 4, 6. Now go to the 6th one. It says valid invalid, it says 0. That means you can't translate because it is not in the physical memory. That is why it says valid invalid bit is 0. And that is why it's just usually in this example, they have taken 0, 0, 0 for all the invalid situations. Okay. So that means that particular page is not in the physical memory or it is not mapped to a frame. Okay. Right. So these are some advanced questions I have added. And also the examiner can sometimes confuse you also. Sometimes the examiner is not giving the information in very brief manner. Sometimes he is just assume that you will understand. That can also happen. But unfortunately, because this is in the structured paper, you have no other option. You can't skip the question, right? You have to do it. Because structured paper questions, you don't have optional questions, right? Always you have to do. Right, so let's try to do a past paper question because these questions we can do later. Okay, we can do later. Let's try to do a past paper question, okay? Even we discuss about the process control blocks, okay? Let's see, everywhere it is operating system, right? Everywhere you can see operating system, and this one is also there. Some other third question also operating system related things are there. Fourth question also operating system related things are. Now we can see why I'm doing it very slowly, okay? And why examiner is interested, because a lot of students confused and examiner is really interested in that. Right, so let's do this part. Fourth question, okay? Right, so give it a try. Give it a try. 1 and 2. Read it. Read it. It's very easy. Right. So let's read it. Okay, let's see. An operating system uses process control block, PCB, to maintain important information about each process. Obviously, right? Process number, process state, open files, that the pointer where the last statement's memory address, right? The registry values. Yes, because the next time when that process got a chance to execute, it will be read and the things will be initialized. Read the following scenario and answer the given question. PL starts a spreadsheet program on a single processor computer, right? Single processor computer. Remember, there are two ways it can do multitasking. Give it to different processors or logical processors or whatever, or even when there's a single processor, it can do time share, giving time slots. So this is to give you the more focus on time slot related things. They have even restricted it to a single processor. So that is to help you, okay? To you, otherwise students might answer it in that kind of way, saying, okay, this process is given to that processor and the other thing is given to that processor. So the examiner is narrowing the possibility, okay? Saying that, no, we have only one processor. To use the budget XLS file that he saved a day before. He also is running a web browser that is used to check his email. That means now he is running two programs. Of course, there can be so many background programs, but officially, at least by intention, he is running two programs. At a particular time, the operating system changed the process state field in the PCB of the spreadsheet process from running to blocked. Give one likely reason for that transition. So why it is going from running to block? Because remember, it goes from running to block, not ready to block. So that means the program is now waiting for a input output operation, right? Answer is correct. Now it is waiting for a input output operation, right? So let's see whether we have the marking scheme. Right, so they have given so many, right? Spreadsheet process requiring to read a file, because that is input output operation, right? Requiring to write to a file, doing an input, doing output, right? When we say input output, either user input output, or maybe file input output, or maybe communicating with a printer or something, or any other thing, okay? Right, so any one of, right? Any one of, right? You will be getting the marks. Right. So when the state of the process changes, running to ready, right? Running to ready, the value of the machine registries. I told you that machine registries are stored in the PCB of the process. I told you that, right? When it goes from ready to running, it has to copy the values in the registries to the PCB. Why? When the next time it is given running state, it has to restore the registry values and continue the execution from there, right? Why is it important to store them? Because next time when it is executed, those registry values has to be restored so that it can execute from that point onwards. So try to explain it in a very simple, clear, right? Even short way. Don't unnecessarily explain also, right? Make it simple, clear, short, okay, up to the point. So then the person who is marking has no issue giving you the full marks. Because if you are writing too many things, that means you are not very sure. At the same time, if you are not writing the full thing, again, the examiner cannot give you the marks, full marks. Right. So now let's see the answer. So that when the process starts running again, it can start from where it stopped. Right, 1 marks, process can start again. 1 marks from where it stopped. You can see. Otherwise, you get half a mark. So I gave you the full. I am getting the full marks. Right. When it start again, it can. Right. When the process is given another chance to run, it can. The processor can execute from where from the current position or current location. So in order to do that, it needs to have it needs to restore the registry values, because when the next process runs, the registries will be cleared and it is restored with the other processors previous states. So therefore, registry is common thing. It has to be clean up. It's something like one person drink water, then the other person is going to drink water using the same glass. Same glass. Registries are something like set of glasses. Right. So this is file handling. Okay. So this question is very popular question. Okay. Right. Read it properly. A block size of a disk is 4 kilobytes. Remember, files are kept in blocks. So these blocks can be read to the memory. This is a file question, not a memory question. Portion in its of its file allocation table starting from block 300 at a particular time is shown below. Okay, remember I told you that in the hard disk we have blocks. We have blocks. A file may not be fit into consecutive blocks. Then we call it contiguous file allocation. So that is one approach operating system may try, but that is not always the case. Sometimes contiguous blocks are not available. So in that case, it must be having one approach is at the end it says, where do you have to find the next block? How do you call that kind of allocation? We did it last time, last week. How do you call that? There are three allocations. I told you that the second part is the one that is needed for your exam, right? There are three type of allocations. First one I already told you, contiguous allocation. Contiguous allocation. That means if it is 300, the rest of the file, if the file is still bigger than the 301, 302. So in order to do that, you must have free space. When you are allocating a file, you make sure that few more space is available so that in the future, if it is getting bigger, you have space. So that is called contiguous. What is the second one? Anyone? What is the second one and what is the third one? We did it last time. Right, linked list. Right, linked list. So that is another one. What is the other one? Now we had three. Linked list. Next one, we discussed three. Contiguous 1 and 2, maybe the first file, this file 4 and 5, etc. Linked list means at the end of this block, it says this is where you have to go to the next one. Say at the end of block 1, it will say, okay, so now you have to visit the block 5 because the rest of the file is in block 5. Then at the end of the block 5, it might say, okay, you have to go to the block 8. So that is called what? Linked list allocation. Now you can see that this question is pretty much linked list. Okay. So what is the third one? Index allocation. So in index allocation, when you are accessing a particular file, right? When you're accessing a particular file, you have to go to that index field, and there they will direct you to the block. Usually it is for a record. You have to go with the record now, right? So then when you usually the primary key or the key field, when you give the key field, there are calculations. There's a way to do the calculation called hash algorithms, and it will say you have to go to this block, and there you will be having the record. Maybe for another record, it will be another block. So that is called index allocation. Now you can see this question is pretty much linked list allocation because you can clearly see that there is a question. After 300, it says 303. And in 303, it says go for 304. Right? And 304 say -1, and they have given note and say the last block of the file is indicated by -1 because different file allocation systems might use different concepts. But the concept is now, therefore, the examiner has explained you that if it is -1, that means the file is now over. Okay. Right. And the block size of the disk is 4 kilobyte. That means this is 4 kilobyte. Every block is 4 kilobyte. Right? 4 kilobyte, 4 kilobyte, 4 kilobyte. Okay. Right. Now what is question? Now read the question again. The block size of the disk is 4 kilobyte. A portion of the file allocation table starting from block 300, right? At a particular time is shown below. It gives the blocks of the maximum.py. This is a Python file. Okay. Forget about the file name. So this is related to the where this maximum.py Python file is saved. So therefore, you can see that first you have to go to the block number 300, right? Block number 300, because this is per file. You get this kind of thing for one file, one table, another file, another table. So this is for this file. So therefore, it starts with 300 block. Then it rest of the stuff is in the block number 303. Sorry, block number 303. Sorry, does it say the starting point? No. Do they say the starting point? No, it says starting block is 300. Okay. So therefore, you have to start from here. And then the rest of the stuff is in 303. Then it says 304. Therefore, the rest of the stuff is in 304. There also the data is there. And it's and 304 block says that is the end of it. You don't have to go to another place to search. If you are looking for something, and if you have, you may have already found it. If not, it is not there. You don't have to go somewhere else. Okay, right. So now what is the question? Write down the value of an important number that will be stored in the directory entry maximum py file that will help the operating system to locate the blocks in that file. So what is the answer? Write down the value of an important number that will be stored in the directory entry for the maximum.py. That will help the operating system to locate the block in that file. So obviously, operating system must know for each and every file what is its starting block, because that is where you start looking at. So therefore, what should be the block number? Block number 300. So maximum.py maybe 300, maybe some other py, maybe it is here 302. So once you go to the starting point, then you can go through, right? So what is the answer? 300. Let's see the answer. Oh, why it is saying 301? 301. Is it 301? But it says 300, right? Block 300. File allocation table starting from portion of its file starting from block 300. Okay, let me erase this and see. Starting from block 300. I think what they have mentioned is, sorry, I think I misread the question. So what they say is not the file is starting from block 300. The question, what the question says is, what you have given is the file allocation block starting point 300 portion is given, not the file is starting at 300, right? Not the file is starting at 300. So yeah. So what they say is, what I have given, or the question what the examiner says is, I have given you the file allocation block table starting from 300 entry, but I thought it is the file is starting from 300, right? No, right? No. So it says I have given you the file allocation table starting from 300. That means not the entire thing. I'm just giving you starting from 300. Okay. I think that is what the examiner says. Okay. So this is, I told you this is a confusing because the examiner has not clearly mentioned, right? I told you that sometimes the examiner is really fussy. So that is one of the reason why this question is difficult, right? So now there's no way you have to understand, you have to guess it. You have to guess it something like this. You have to assume that this is the file allocation table for this file. It's sort of unfortunate situation. Okay. So then you have to look at some logic. Okay. Now this guy says 300 says 303. So therefore from 300 you have to go to 303. Then 303 says 304. So therefore you have to go there, and it says -1, therefore you don't have to go there, anywhere else. But there's another one, because it says this is the file allocation table for this file. So therefore this 301 is asking to go to 300. So therefore you have to assume that you have to go like this also. So now you can see that if this is the entire block, the file allocation table for this file, we have to start, because no one is asking to come to 300. If no block is redirecting you to 300, this must be the starting point, right? This must be the starting point. That is the 301 must be the starting point. So then it is asking you to go to the 300 to look at the next portion, and it says go to 303 to look at the next portion, and it says go to 304 to look at the next portion. So therefore your operating system must keep 301 as the pointer, right? In the under maximum.py file, it has to keep 301 as the pointer, because the operating system can't go and solve puzzles and find it. It must be straight away come to the starting block. So that is the question they have asked in a very fussy way. Actually, I also got confused, right? So here the starting from block 3 means what they say is I have given you the fact table starting from 300. Okay. So by looking at this only, you have to find out what is the first one. So therefore, your operating system has to keep 300 as the reference here, because then it can just go from there here. Okay. Right. So little bit confusing question. Right. Next one. Assume that additional improvements are made to the maximum.py. That means they have changed the file, so added some more content. Py file that the result in that results in its size becoming 20 kilobyte. Now it has become 20 kilobyte. Okay. What changes are needed in the FAT for this purpose? Right. Now remember, each block can keep only 4. Now earlier 4 kilobyte here, another 4 kilobyte here, 8. Okay. Another 4 kilobyte here, because it says come here 16, sorry 12, another 4 kilobyte here, and it says that's the end. End means this one is also used, right? This one is this either full block or half of the block or part of the block is used. So maybe earlier it is 4 4 4, maximum 4 here, that is 16, maximum 16 kilobyte. It can be less than 16 kilobyte, but definitely more than 12 kilobytes, because it has pointed to this one, and this one is says no, you don't have to go anywhere. So that means 4 4 4 and something less than 4, maximum 4. That means maximum 16 kilobyte. So now it says your file is 20 kilobyte. So that means you have to go for another full block. Another full block. Now you can see this block is available. This block is available. So therefore, not most probably, we have only one option now, because there are no other free blocks there. So therefore, the table has to say here, rather than -1, right? You have to say now you have to go to 302. So that the file will be there. And here maybe you can say -1. Here you can say -1, because that is the end of it. Because 20 can be kept in 5 blocks, maximum 5 blocks. So you have to write down that as answer. Okay. Yeah, linked list and index. Right. Now let's see the answer. Right. Entry in 304 changed to 302. 304, we have to change from -1 to 302. Okay. And entry in 302 must be -1. Entry in 302 change to -1. So that is how you get the full marks. Okay, I hope you got it. Right. So now you have the memory address translation question. Right. So I am not going to do it, because I want you to give it a try. Take this very seriously. Think about it. Think about it. Think about it. Think about it. It doesn't matter whether you spend half an hour, right, and try to do this question, and remind me if I forget it. We are going to do this question at the beginning of the next class. Then we will be move into the logic. I think we have to do small part. Then we will do into logic part as well, and maybe still more past question. Okay. Right. So we'll stop at this point. Right. I hope you understood it. This is one of the most difficult topic we did it today. Okay. Right. We'll stop at this point. Right. Thank you.